Hello, my name is William Lofton, and I am doing the video portion for our Group 2 project. This project is covering the linear algebra as well as the data analysis problem. Both of these problems are going to be described in brief detail, and then I'm going to cover, I'm going to go through the problem statement and the algorithm, and then go through the code, as well as describing what each section of the code does and why we get the answer that we do. Anyways, I want to start with the first problem. And this first problem is to calculate the solutions to a matrix by taking the upper triangular form and using back substitution. Now I wanted to pull up this page right here on upper triangular matrix in case you're not in linear algebra. Essentially, you have a form where that looks very similar to this. Often you'll have a 1 and then a 0 and then a 0 and then your answer, or you'll have that is reduced row echelon form. And everything below this one will be zeros, everything below this one will be zeros, and so on and so forth. And so you get this triangular form where you've got ones going diagonally and zeros below those ones. There's many ways of solving these types of problems. One, as I mentioned, is reduced row echelon or row echelon form, which can also be Gaussian elimination by adding the rows together, multiplying, adding different numbers to the rows so that you get your upper triangular form. So now I want to kind of cover the algorithm for the code and go over how it's going to run and what exactly the problem is. So the program will ask the user to input an n by n plus 1 matrix. Then it will validate the size and is the first number that the matrix is not equal to 0. After the user enters a correct form of the matrix, the program will display the original matrix. Then run the uptry function. This function, the matrix will be converted into an upper triangular form, as I'm showing you right here. The function beginning by sizing the matrix and defining a counter to be equal to 1, then a nested for loop that beginning with j equals 1 to column minus 2. After the first loop, we'll run the counter will be k is equal to k plus 1, and the second for loop will run from row to minus 1 to k. This means we will start making calculations starting from the bottom of the column to k. Because k is increasing every time we go into a different column, we make one less calculation every time it does. The code works by multiplying the row in which the number we want to change is located by 1 above it, if it's not 0, and vice versa, and then subtracting those two rows, converting the desired targeted number into a 0. Because this changes all the other numbers in the row, we include an if statement that divides the row by 2 if the sum of this is greater than 1,000. After the function concludes the calculations, the program will display the upper triangular form of the original matrix. Then a validation code will determine if there are infinitely many solutions, one solution, or no solution to the matrix. After determining if there is one solution to the code, the code will run back sub function, which will size the matrix, create a vector of size row filled with zeros, and start making the back substitution. Calculations to determine the solution of the matrix with a nested for loop g and h, and t is equal to 0 every time g increases, the resulting solution will be stored in the vector y. Alright, so now you probably want me to go through the code, and I can show you exactly how this runs. So as I was stating before, we have our input for the n times n by 1 matrix, our for loop to check the dimensions, and if you've inputted the wrong dimensions, this will ask you to re-enter a matrix. And then this checks if the first number is 0, because if the first number is 0, we won't be able to solve our matrix in the upper, or put the matrix into an upper triangular form. This one checks displays the original matrix. This one runs the upper triangular form with the function that we have here. I'm not going to go into too much detail on the function, but this function essentially calculates our upper triangular form. It goes through and runs through the entire matrix and does the calculations until we have the form that we are looking for, like I mentioned before, where we have ones going in diagonal and zeros below those. The back sub is essentially, as I mentioned before, it back substitutes into the columns for the matrix to calculate the upper triangular form. We do validation checks, and this determines this checks our matrix once it's calculated to whether there's infinitely many solutions, no solutions, or there is one solution. One solution would be where you have one x value equal to one number. Infinitely many could be a row of zeros. Anyways, I'm going to run this code and just kind of show you exactly what it's doing. So now it wants me to enter a matrix of n by n plus 1. So I'm going to enter this matrix that I've entered before. And it brings up the upper triangular form. As you see, there are multiple rows of zeros. This upper row here is starting with 1, zeros below that. Everything else became a 0. And the program asked me if I would like to run again, so I'm going to hit yes, and I'm going to enter another matrix. Sorry, I did not have this one right at hand. Error on my part. Alright, so this is a little bit more complicated of a problem. So this shows you the exactly what our code is, and then it does what it was supposed to do when I originally put in my old matrix. The old matrix I set up was just sort of an initial test to see if it's doing the correct thing. So it's giving us our initial matrix that I input here, the upper triangular form, and then it tells us that there is one solution. Anyways, that is, in summary, the upper triangular form code, or the linear algebra portion. Now I'd like to move on to the second problem in our task for our project. This is the bisection method, and yes, I pulled up a Wikipedia page, but it has a very good description, and I wanted to show, I didn't want to read through the description, but I wanted to show the image, and it was a really simple thing to bring up. Anyways, for this problem, essentially what you're doing is finding intermediate boundaries, and in between those boundaries, your code is solving or bisecting the equation after you put in a vector with your equation, and it's finding the roots this way. Now this is a much slower method than, say, I don't know, if you were to take the derivative of this, or not the derivative, if you were to solve it by, say, factoring it or setting the values equal to 0, like say like an f0 type function. This is a much slower way, but it's a very accurate way of essentially dissecting the equation and going through. I wanted to show that there was kind of this example that it's going through and finding the roots for this equation. Now I want to go through the algorithm for this and go through this fairly quickly just so you can get a good summary, and then go through the code and discuss what the code's doing. So in problem 2, we created a function called bisect root, which would take an input from vector a1 in the form of a1, a2, a3, all the way to a to the n, which corresponds to the degree of the polynomial. The code also takes the maximum acceptable error and two starting guesses that bound the root in the solution. The code includes a validation in case the user inputs bounds that are both positive or negative, or both positive or both negative, because your bounds have to have opposite signs. I should have mentioned that before. Then the code asks the user for two new bounds and explains why. Our code then displays an approximation of the root and the maximum error depending on what the user inputs for the maximum error allowed and the number of changes the code took to produce the resultant matrix. In addition to our solution, the code also calculates the maximum error at every change the code makes. Then the code plots the maximum error as a function of its iteration. The code then finds the proper plot to explain this data. The code then calls out a new function called bisect root 2, which will aid the plot before the data and fit, which helps us prove the formula theorem, where A represents the number of iterations and B represents the initial guesses for the bounds. Finally, program asks the user whether he or she wants to rerun the program again. All fairly simple and straightforward stuff there. Now I'm going to move on to the code, close out the previous menu, move on to problem 2. So this while loop is running and basically is going to be the thing that asks if we want to run the code again. Vector is the initial input for the coefficients as a line vector. Max error is the user's input for the maximum error. Lower bound and high bound or upper bound are the bounds that the user will input as a guess for the bounds of the intersection. This is checking if we've input the correct size of coefficients into the as a vector. These are our calculations to determine the high and low bound. And finally, we're giving user warnings that the bounds are either both positive, or if they are both negative, or if they're both equal to 0, or if the bound is already a root. I should have mentioned that equal to 0 is a root. You probably caught that. Now I'm going to run this section of the code. Oh, one last thing that I forgot to mention. and I mentioned it in the algorithm, we are plotting this as well. Go back up to the top. Input the coefficients as a line vector. Let's say 1, 2, 3, 4, 5. Enter the maximum acceptable error. Say 0.0010. Input the lower bound, 0.1 and 0.5. Warning, both of these bounds are positive, so 0.1 and negative 0.5. Whoops. Alright, looks like we got an error from the value that were input. Let me go ahead and check this one last time and make sure that I didn't have any mistakes going through. Oh, I should have mentioned again as well as the code here, the function. The function is calculating our roots, our max error, all positive and negative values. This bisect root is calculating the error in the lower bounds and the upper bounds. So that is basically everything we have for our code. Thank you for watching.